are lost in this section.
You are lost with what?
In this section.
With this?
Yes, in this section, yes.
Well, I will not include it into exam. This is for your knowledge. Look, there are two basic ways to give you knowledge. I can be mathematically precise and straightforward, and then I will be able to cover only very little part of physics. On the other hand, I can be as much precise and straightforward as possible in describing some important part and just review you what happens in all other domains of parameters, just for completeness of understanding the picture. So I prefer to do the second. Think to let you know that the static susceptibility is not everything which we can access, and the dynamical response function contains everything, all information which we learn moving step by step in the calculations. And in principle, it contains even more information that we can digest and which we can discuss deriving during the course of lectures. Okay, so spin subject to time-dependent magnetic field. Bloch equation. Let's consider the Hamiltonian minus m times t. Now, I will assume that h has a component h node, and I will take z direction along the static component, and there is a small time-dependent component h1 t along x direction. So this is x, this is y. So my magnetic field H is equal to h1 t 0 h naught. So magnetization is G mu bar sum over n Sn. And as I said, the Heisenberg equation of motion, Sn dot let's write in the components. Alpha is equal to I over H G mu bar, and here it's epsilon alpha beta gamma that's not being hard. It's I over H, commutator of the Hamiltonian, and S n alpha. Okay? If I plug in the Hamiltonian, which is written in terms of susceptibility, I have to use the fact that commutator of Sn alpha Sn beta is equal to I epsilon alpha beta gamma Sn gamma delta n. So this is how different components of spins commute on the different sides. So if n and m are not equal to each other, I have this commutator equal to 0. If somehow they belong to the same side, then the commutator of two of components is expressed in terms of the short one. Then I will plug in the Hamiltonian and use these commutation relations. And please make this exercise because the technical point will be to make convolution of two antisymmetric symbols. Are you familiar with this? Epsilon alpha beta is Levi segments. So you know that if you take, say, epsilon alpha beta gamma, epsilon alpha mu, I use the same notation, which means that repeating indexes assume summation. So this is sum over alpha. Do you know what it is equal to? It's equal to determinant based on the canonical symbols. Beta mu, delta beta mu, delta gamma mu, delta gamma mu. So this is, well, if you do it, then you arrive at an equation which tells you that m dot is equal to minus gamma m h, where gamma is equal to Bohr magneton times G divided by. So this equation describes you dynamics of magnetization, and this is known as Bloch equation. Plays very important role in description of dynamics of spin, and very widely used now when people study dynamics of qubits. For example, in order to construct hardware for quantum computation. Qubit is a quantum bit, as you probably heard. Okay, let's write down this equation component by component. So you see that here there's a vector product. So m times h is determinant x, y, z. I assumed that my magnetic field is h1, 0, h0. And for magnetization, since there is a big component applied along z, and h1 is assumed to be much smaller than h0, I will also assume that there will be magnetization along z direction, slightly corrected by time-dependent addition. So mx and y and mz are functions of time, which I'm going to find by solving this equation. And all time dependence is generated by the magnetic field. So component by component, I'm going to write three equations of motion. Sometimes it's called equation of motion for magnetization for mx and y and mz. M is equal to mx, my, m node minus mz. As I said, I subtracted big time independent component, which is a response to big time independent magnetic field along this direction. dmx over dt is equal to minus gamma h node and y. I open this determinant. You see that there is only this term. Y component of field is absent. dmy over dt. Are you understanding what is equal to minus gamma h1 m naught minus mz. This one plus gamma h naught mx. This one. And then dmz over dt is equal to gamma h1 my. So you see that there is a system of three coupled equations for x, y, and z components of monetization. What I want to do now is to linearize this equation. At this very moment, they are not linear. What I will do, I assume that mx and y and mz small are much smaller than m naught. Any of them. And on the other hand, as I said, h1 is much smaller than h2. Look at this equation. The right hand side contains h1 and my, and the left hand side contains mz. So it's square of small parameter and its first part. So therefore, in order to linearize the equation, I replace it by 0. The same way I drop mz from here. So what I see now is linearized and simplified system of equation, which immediately tells me that mz is a constant. But remaining system of two equations is described in terms of mx and y mx. So I exclude one of the components.
Why do we need that in this my first equation?
Sorry? H naught is big. So H naught is big. So therefore, it has a smallness in the left hand side and the same order of smallness in the right hand side. The same here. H1 is small. Therefore, M naught is big. I keep this. And H naught is big, Mx is small. So it's again the same smallness. Here, it exceeds my accuracy. So therefore, I have to put it equal to 0.
Can I ask a question?
Sure.
I mean, why need linearize? I mean, you can solve it that is complete difference.
Try to solve it exactly, if you can.
So,
It's a system of three coupled equations.
yeah, we can decouple them in such a way. For example, for the first equation, we can find if we differentiate the first equation. I mean,
Right.
what's the sense to?
I will be glad to discuss with you solution when you show me. Okay, good exercise. Try, and this is how scientific works initiate. You think that everything is simple, you start to produce your ideas how to solve, and then you see that life is more complicated, but you push hard and sometimes you get some interesting result. Challenging question.
So linearizing means to solve the question? Not
No, what I suggest, you go take a piece of paper and take a derivation and show me. Because I'm not ready to discuss a speculation. If we substitute this and do it, you have a program, you have a vision how to do it, I encourage you to do it. Maybe you're right. Okay? Why? It's a very nice thing. As I said, this is how research program works. Okay. With this remaining system of two coupled equations, it's very easy how to do it. For example, we can differentiate this equation with respect to time. And if we do it, h naught doesn't depend on time. h1 is arbitrary function of time. I'm not specifying what the function is. So therefore, for example, from this equation, I will get d2 mx squared over dt squared is equal to minus gamma node h node dmy over dt. And then I use the second equation in order to exclude my. And what you see, and what happens is you will have an oscillator with a driving force. So there is an oscillator. Let me introduce variable omega node, which is cyclotron frequency. It's gamma h node. So it's g e h node over 2mc. I plugged in Born-Newton, and since for electron I'm working with electron, g is equal to 2. So this is e h node over mc. So this is a cyclotron frequency. So this equation reads, this is minus omega node my, and excluding my, I have a question mx double dot plus omega node square mx here is equal to what omega node gamma m node times h1 t. So then, in principle, if I specify the form of magnetic field in time dependent, I can find a solution if I'm lucky. But in order to solve this linear differential equation for arbitrary function h1 of t, one needs to construct a wave function of this differential. This is what Ganesh will tell you how to do, how to write a solution of this differential equation for arbitrary function h1 t, of course particular solution, because the solution of homogeneous equation is known. It's just sine plus cosine. Okay, but I will solve you the problem for particular case h1 t is equal to h1 cosine omega. Okay? Then, as I said, homogeneous solution is mx is equal to a cosine omega node t plus b sine omega node t. And for this simple equation, I will look for particular solution of non-homogeneous equation mx tilde at some constant of the same form, cosine omega t. So if I plug it in here, what I will have, omega node square minus omega square times c cosine omega t is equal to omega node gamma m node h1 cosine omega t. So I immediately find a solution which I will add here. So c is equal to omega node gamma m node h1 divided by omega node square minus omega square. So again, now put it into the bracket. So it's plus gamma omega node H1 M node cosine omega phi divided by omega node minus omega squared. Okay? So this is solution, of course, using this equation. I can now find my. I just invert it, so my is equal to minus 1 over omega node times dmx over dt. So what I need to do is differentiate this solution. Of course, if I postulate some initial condition, what my magnetization was equal to at time equal to 0, I will find the complete solution of the problem. But what I'm going to tell you now is, look, we have applied AC magnetic field in x direction. And what we see here is nothing but susceptibility. Because in linear response, the susceptibility is a coefficient of proportionality between applied in x direction field and induced magnetization. So, and you see that this susceptibility does have poles corresponding to the oscillations with the frequency which is omega naught. So this is what I was saying to you when arguing that dynamic susceptibility has poles, and in this case there is no Q dependence, the field is uniform, and this is just a constant. This is Larmor frequency, which describes a precession information. If you do it with a Green function, you will see some causality, namely this pole is shifted in imaginary plane, which actually tells you that your response is retarded function. So you first apply a field and then you get a response. And this is what you are going to discuss in great details with Dinesh. But believe me, the Green function method is extremely powerful tool to solve this kind of equation. Discussing causality, you will also see that susceptibility actually is a complex analytic function, is a complex function on its arguments. Namely, the susceptibility has both real and imaginary part, and since we are dealing with causal objects, then we may arrive, for example, for very important relations between real and imaginary part, which are known as Kramers-Kronig relations.
So I have a question about, so first of all, what is this omega? So this omega is frequency of what?
Omega node is
the omega.
Omega is a frequency of external field. I assume that external field is applied with some frequency omega.
Okay. So now if this is the frequency of the external field is equal to this Larmor frequency.
Then there is a resonance. It's an interesting question. What happens if the omega is equal to omega naught? Then you will see that susceptibility has two delta functions of x, corresponding to, so as I said, susceptibility. What I'm saying now is susceptibility chi xx is a complex function. It has real part and imaginary part. And what happens if omega is equal to 0, then imaginary part will consist of two delta functions. So your system is in resonance. And this is what is measured. I mean, this is one of the powerful tools to measure spin relaxation effects. Namely, of course, this equation for magnetization do not assume any relaxation processes which happen when spin interacts with other spins. But in principle, all excitations in the systems are damped. And what resulted in delta function here, in reality, will be broadened and imaginary part has the form. So measuring the echo, for example, in a magnet, when there is a pulse applied to the system and then another pulse after some time, and people collecting delay between two pulses passing through the system, allows you to measure the width of the resistance. So this is experimental, accessible information, and moreover, this is how experimentalists measure some parameters of your system. Yes, the only comment I would like to do is the last one, is what happens with this equation. I should probably write it down here. dm over dt is equal to minus gamma h times m, sorry, m times h. What happens if I'm back to my Heisenberg magnet? If I have a ferromagnet? When we discussed the magnons, we interpreted it some kind of spin density wave. But one can also think about magnetic field appearing due to molecular field, which varies from point to point, such a way that magnetic field is almost uniform. So magnetic field, total magnetic field in the system is kind of H naught, which is associated with the molecular field in the vicinity of saturation of magnetization curve, plus I will write that it is related to magnetization and its special gradient, x alpha, x beta. So you are in a minimum, like with phonons, you expand your magnetic field being in the minimum, taking into account small deviation from the minimum value. So if you plug it in here, and solve the equation for magnetization, you see it is not linear, because H also contains magnetization. You will macroscopically derive a magnet. Because what do you have here? You have second derivative. You take a Fourier, you get k squared. What do you have here? You have a first derivative. When you take a Fourier, you will get omega. So, using this Bloch equation, generalized for the case of special gradients of magnetic field related to magnetization, one arrives at macroscopic derivation of the magnons, and the equation is known as Landau-Riefenstahl equation. So equation, which I will write it down, well, let me write here alpha, sorry, some constant a alpha beta, because I need to have a scalar here. The equation that dm over dt is equal to gamma r alpha beta d2m over dx alpha dx beta times m naught is called Landau-Riefenstahl equation. So one can derive the magnon dispersion from this equation very easily. You may ask me how it happens that when you take a Fourier you have I here, but you see that you have a vector product. The same way you have to exclude mx and y component out of plane. You so to say square your equation, and actually the dispersion which you will get is omega square is equal to lambda k square square. and subtracting square root, you arrive at dispersion minus. So this is how to get the information about the excitation spectrum, as I said, analyzing susceptibility. And this is also the way experimentalists measure that. Because this field is controllable, one adds AC component, and actually applying small AC field, one can test and measure the response function in the system. Okay, that's all for today. I think we will not spend more time for magnetism. Of course, when we discuss Konda effect, its magnetic impurity, we will speak about spins. But as far as collective state and excitations in the magnetic system are concerned, that's all what I plan to say you on this subject. Any questions?
I have a question about the symmetry breaking of the magnetization. Like we are actually considering the shape anisotropic systems. Like if you consider a perfect sphere in 2 dimensions, and instead of a sphere, if you consider a strip, so.
Well, sometimes your system is anisotropic from very beginning. Sometimes you also have spin-orbit interaction, which tells you how spin degrees of freedom are connected with orbital one. Sometimes you can apply stress to the system, like you said, to have a stripe or whatever, and then of course the spontaneous symmetry breaking happens in a direction which is already preferable. But if we are in an isotropic situation, then of course the coordinate, the space coordinate, do not know anything about spin coordinate, and the symmetry breaking is initiated by magnetic field. So you should assume that we are applying some magnetic field to the system, little one. It causes the symmetry breaking, and then we can switch it off. It actually tells us in which direction we should break our symmetry. But of course, in reality, you have crystalline axis, you have crystalline electric field in the system. Sometimes you have also magnetic field existing in the system. So system knows where to go. And moreover, there is plenty of other magnetic phase transition, like flip-flop, where your spins being arranged along one direction and then flip in the plane. Some of this phase transition are first-order phase transition. So if you are interested in a variety of magnetic and metamagnetic transition, which also exists, and connecting one magnetic phase to another one, as I said, there might be transition between 2 differently ordered magnetic states in the system. Then I would probably recommend you some book about magnetism, which contains a lot of details.
By the way, I think for Eisenhower, the symmetry is discrete.
Yes.
So there's no elementary excitation.
Well, symmetry is discrete. There is no gapless excitation. That's true. So all excitations are gapped, except you say in the quantum critical coil, where at one point of phase diagram, where 2 different ground states come together. This is quantumizing mode. So to say in transverse magnetic field, you can close the gap, and this is, as I said, essence of quantum phase transition. But you are right saying that if the symmetry which is broken is discrete, it is not subject of Goldstone theorem, and no gapless mode is expected in this mode.
So, which book is good for quantum?
There is a book of Sajdev, which is called Quantum Phase Transition. Sugar Sajdev, Quantum Phase Transition. And it actually considers this Eisenhower model in great details. Okay. question on this fermionic bosonic transformation. Well, there is one subject which is called supersymmetry. And when both fermion and bosonic states are present, in principle, one can make a transformation which rotates from one sector to another. But this, I mean, is far beyond any advanced course. When I used to teach advanced quantum mechanics, I tell people about supersymmetric quantum mechanics, which, if you are interested, is a very nice thing. For example, oscillator, so spin subject to magnetic field, is a supersymmetric problem because one can identify fermion with a spin, and one can identify boson with oscillator-like behavior. Here, so I can recommend you some literature about supersymmetry. But as I said, this is very interesting but also advanced.
What do you think about the pen and the rank for supersymmetry?
Sorry?
The pen and the rank. The book of the pen.
Which book? No, it was rather a review paper. Well, the key person in this field was beaten. So this great physicist working in string theory, and because the idea was to have and this theory, this supersymmetric quantum field theory. But Beaton's supersymmetric quantum mechanics was developed in the early 70s. There is a book of Schwab on quantum mechanics. You can read it there. But I would rather recommend you some review articles on supersymmetry if you're interested.
So, tell me
Name is Schwab, the textbook. But you better read the original paper of Wheaton, which is very nice.
because I was told that the books of Weber is very difficult to understand.
No, in principle, think is very simple. As far as one-dimensional quantum mechanics is concerned, for example, you know that there is a barrier. Let's consider scattering on the barrier, which has the form 1 over cos squared x. So this is, well, you know, this is ux as function of x. And we consider scattering of the particle, you know, in quantum mechanics, particles scatter even being in continuum. They fill the barrier. It appears that there are special values of energy where this barrier doesn't reflect particles at all. So the reflection coefficient is equal to 0, which is very strange. And people didn't understand this for a long time. It was known. It is written in Landau-Licht's book, for example, that there are some values of energies in continuum spectrum where the barrier doesn't reflect. But the reason of this behavior was not understood. But only with Wheaton, it was shown that this potential is so-called supersymmetric potential. So there is a symmetry between the fermions and bosons, so to say. One can construct the Schrödinger equation. I don't want to enter this theory.
I didn't understand why you say that. People don't understand. Because I just think if we solve the Schrödinger equation, then we will get
Yeah, we see that it happens, but we don't know why. What kind of symmetry is behind of this interesting behavior that barrier becomes non-reflecting at all. So this symmetry is kind of supersymmetry between fermions and bosons, which allows to construct some supersymmetric potential, superpotential for fermionic and bosonic problem. And then
But to what I understand, if the potential is 96, it should also have, it's a square well, it should also have written property.
No, not all potentials, first of all, have the same property. If you calculate reflection and transmission coefficient just by scattering from this barrier, you see that usually this reflection and transmission amplitudes or coefficients are continuous functions. So only for very high energies barrier is exponentially small reflecting. But for very few potentials, you can have energies for given values when reflection coefficient is exactly 0.
I don't know about this well, but if the potential is 90, then
Yes, so.
then the transmission coefficient will have something like this.
The function of what?
Energy.
Mm-hmm.
This
Mm-hmm.
is something like this one.
Okay.
This exact.
Okay.
So, I mean,
Then there is also supersymmetry in this potential too. One can construct corresponding supersymmetric problem in bosonic and fermionic spectrum. What I'm saying is, look, let me write the Hamiltonian for system for one electron in magnetic field. So the Hamiltonian is H omega, and here it's n oscillators plus 1. So this is energy, sorry, if I write a Hamiltonian, I will write n bosons plus 1 half. And then there is a term minus sigma minus Zeeman term minus h times sigma magnetic field. If you write this down, you will get h omega, so with the sign plus, h omega. Now I put more magnetons, and here, since this is a Pauli matrix, you will write this is n fermions, something which is either 0 or 1, but since Pauli matrix Z is plus 1 half, minus 1 half, minus 1 half. So this behaves like a spin. If n number of fermions is equal to 1, this is 1 half. If number of fermions is equal to 0, this is minus 1 half. So therefore, your total Hamiltonian of spin in magnetic field is n bosons plus n fermions. So you see that this Hamiltonian is symmetric with respect to change bosons to fermions. So this is supersymmetric Hamiltonian. And problem of electron in the magnetic field is a supersymmetric quantum mechanical problem. Moreover, the ground state, so here we had 0-point motion, so the energy of oscillators starts from this h omega half. Here, the 0-point motion in the fermionic spectrum is compensated. So ground state is non-degenerate and corresponds to zero energy. But then, acting on ground state, one can construct excited state in fermionic and bosonic spectrum, and this is, in principle, supersymmetry means that your Schrödinger equation, which is a second-order differential equation, can be transformed to first-order differential equation. And then, doing that, you construct a solution in both sectors and use this supersymmetry property. So there are some Hamiltonians, you asked me about transformations. There are some Hamiltonians which are supersymmetric, and when rotation in one sector will affect another one. And one can construct a combination of fermionic and bosonic operator and rotate it in both sectors. But for Hamiltonian, which is just bosonic, it doesn't make any sense to rotate it from fermionic side. There should be some symmetry. And this is a supersymmetry.
I hear about supersymmetry in kinetic physics, but I didn't know.
Are you interested in the supersymmetry or what? Where did you read it?
No, because when I was in university, I like to study high energy physics.
I see. But there is a deep connection with, say, nonlinear differential equations like Korteweg-de-Vries equation, which describes the propagation of solitons and supersymmetry. So, you know, if we enter a business of supersymmetry, and I'm not an expert in it, there are many things which are so nice and wonderful and connected between different fields of physics that. You're welcome. Waiting for me? A question? No, I thought I would think about kind of problem which we may start to discuss. Let's do this thing. Scandal, the coordinator of Professor Scandal of the program, suggests to meet next week together, and all staff members of the group meet and discuss what they're doing, introduce you to our research project. Let me think, since I'm now in a very tough schedule, let me think about possible problem till next week, and then we probably discuss what's going on. At this very moment, I'm not ready to suggest anything. So I'm sorry. It's a really very tough schedule of giving 4 lectures a week. I would prefer to have less. Because I also believe that I'm moving very fast and maybe not everybody is able to follow me. But what's your impression? Do you understand what we discussed? I see. Good. Good.